Okay, let's go ahead and go over today's warm-up question, which says, which has a greater acceleration? And you've got two options. Option A says a car driving down the freeway at a constant speed of 65 miles per hour. And option B says a cyclist pedaling from rest to reach a speed of 10 miles per hour. So which one would you say has a greater acceleration? Yes.
The cyclist, because the car's driving at a constant speed, it's going to slow accelerate.
Perfect, and I know y'all probably didn't hear her, it was a little quiet, but that's okay. She said the cyclist because the car's traveling at a constant speed. And that is true. The car, although it is moving faster, has acceleration of 0. Its velocity is faster, but it's not accelerating. And so the cyclist is going to have a greater acceleration because he is actually accelerating, whereas the car is not. So again, please answer that question in that Google form, and then you can just close. It should say saved up at the top, or like progress saved or data saved, something. There's like a little cloud. So when you open it up again next week to answer some more questions, it should save your progress. But you do not need to submit it yet because we haven't answered the rest of the questions. Today we're going to go over some notes, acceleration notes and concepts, and so I would encourage you to have some paper out. And then you are going to have a homework assignment, 202.1 Acceleration Concepts Problem Set, which we can take a look at once we finish with the assignment today. Okay. So we already went over this one, but the cyclist is going to have greater acceleration. Again, this is a common misconception, but acceleration is not the same thing as going fast. Just because the car is faster does not mean that it has a greater acceleration. Okay, we're going to go over a lot of misconceptions today, and I know that yesterday you guys kind of got introduced to the unit by gathering some data in a digital lab, so hopefully some of this you're like, oh yeah, I saw that yesterday, and we can kind of fill in some of those gaps. But acceleration is not the same thing as going fast. Acceleration is the change in rate of velocity, and that means that it is a vector. Because velocity is a vector, so is acceleration, because we are talking about changes to velocity. Acceleration will occur when an object speeds up, slows down, or changes direction. Because it is a vector, if you turn, that is acceleration because your velocity has changed, because again, direction is a component of that velocity. So speeding up, slowing down, and changing direction. That's also a misconception, is that people look at that word acceleration and they think that it only means speeding up. But it doesn't. If something slows down, it is also experiencing acceleration. Okay, so how about this? Which has a greater acceleration? Similar to our warm-up. A car speeding up from 45 to 60 miles per hour as it enters a freeway, or a car slowing down from 45 to 30 miles per hour in a school zone. What do you think? Okay, we have a guess for B. What do you think?
I thought it was equal.
She thinks they're equal. She thinks it's B. We've got two answers. What do you guys think? Anybody else have a thought they want to share? They're equal, and I heard A. So we have all possible choices. These are going to have the exact same acceleration. The magnitude of the acceleration is the same. Assuming both happen over the same amount of time, which I probably should have put in the question. Okay, if both of those changes in velocity happen over the same amount of time, then they're both the same magnitude. Okay, they both have changed their velocity by 15 miles per hour. It's just one of them went faster by 15, the other went slower by 15. But that is the same acceleration, the same magnitude, again, if they're happening over the same time period. Again, that's the other misconception I just mentioned. Acceleration can be speeding up, or it can be slowing down, or even just a change in direction. Okay, so just because you're getting faster doesn't mean your acceleration is more than this person who's getting slower. Here is the equation. We already have the definition. Acceleration is the change in rate of velocity. It can be calculated by the formula A equals delta V over T. In that equation, A is acceleration, and the units that we use for acceleration are meters per second, which can also be written as meters per second squared. Delta V is change in velocity. You guys should be familiar with that symbol, that delta, from your math class. It means change in, and so this is change in velocity. And that can be found by taking your final velocity and subtracting your initial velocity. So for example, in that last question, if you go from 45 to 60 and you wanted to find the change, you would take that 60, that final velocity, and subtract 45, and you'd get positive 15. Okay, the change in velocity should be in units of meters per second. And then the t in the equation down here in the denominator is time, and it does need to be in seconds because your units need to be consistent. Okay, if this is meters per second and this is meters per second, these need to be in seconds. And obviously if any of those things don't match, then you would have to do a conversion for whichever one you need to get to match the other ones. The sign of acceleration, whether it's positive or negative, indicates whether the change in velocity is increasing or decreasing. And we're going to look at that some more too, because there are a lot of misconceptions about what positive and negative acceleration mean. Okay, because some of you might be thinking now, oh, well, that seems easy. It's speeding up or slowing down, and you are wrong, because that would be the misconception, and we're going to get to that in a minute. All right, a positive acceleration indicates that the change in velocity is positive. Here are the two scenarios where you can have that. This occurs when an object speeds up in the forward direction, but it also occurs when an object slows down in the backward direction. Okay, and that's probably easier to see with some data. Now, the first one I think y'all all agree with, that seems like it would be positive, speeding up in the forward direction, but here's some example numbers to show you. So here's my time, 0, 1, 2, 3 seconds. Here are some velocities, 0, 2, 4, and 6. My change in velocity each second, according to this data, is positive 2. Okay, and so my acceleration here is positive. I am getting faster. I am moving forward the whole time. Okay, however, look at the data for this. When an object slows down in the backward direction, here's some example data. This object is moving at negative 12. And then at negative 9, and then at negative 6, and then at negative 3, and if we continued the trend, it'd be at 0 in the next second, but it's slowing down. It's getting slower, closer to 0. 0 is stopped, so the closer we get to 0, the slower we are going. Okay, and if you look at the change, what is the change in my velocity each second here? Is it positive or negative? The change is positive, right? From negative 12 to negative 9 is a change of positive 3. From negative 9 to negative 6, positive 3. So it's changing positive 3 meters per second every second. That, by the way, is where that unit comes from, meters per second every second. Okay, and so this is also positive acceleration. So positive acceleration does not necessarily mean you are speeding up. It can, but it just means that your change in velocity is positive. So it could mean either of these two scenarios. A negative acceleration indicates the change in velocity is negative. And again, just like positive acceleration doesn't necessarily mean speeding up, negative acceleration doesn't necessarily mean speeding down, although it can. An object that slows down in the forward direction, like this one from 8 to 7 to 6 to 5, has a negative acceleration. In fact, this particular data is showing that I have a change in velocity, a change in rate of velocity of negative 1 meters per second every second. And so this would be an acceleration of negative 1. That is, of course, negative. Okay. However, so is this. An object speeding up in the backward direction. Look at the data. I think the numbers make this easier, so I would add them to your notes, by the way, for both of, the previous slide and this one. But again, look at my velocity. 0 means I'm not moving. So obviously this is faster, negative 5, negative 10, negative 15. I'm getting faster in the negative direction. And my rate of change in velocity for this example data is negative 5 meters per second every second. That is a negative acceleration, and yet this object is speeding up. Okay, that is one of the most common misconceptions that students have is they look at negative acceleration and they say that means slowing down, and they look at positive acceleration and they say that means speeding up, and no, it does not. Okay, it can, but it doesn't necessarily mean that. So again, these are the 4 possible examples that you'll see for your data for an object that's experiencing acceleration. So we got 2 examples of positive, 2 examples of negative acceleration. Make sure that you are familiar with them. All right, so let's look at this example question. It says, let's say a car is traveling at 20 meters per second and enters a freeway ramp where the car accelerates at a rate of 5 meters per second every second, which can be written as 5 meters per second squared, until it reaches a speed of 35 meters per second. What is the car's speed 1 second after entering the freeway ramp? Well, if it's traveling 20 meters per second, then 1 second after it starts to speed up and its rate of change is 5, then it should be at 25, right? We're just going to add that on. Okay, so there's my initial velocity, and after 1 second, I'm at 25. Okay, what about 2 seconds after? How fast would it be going? Yeah, 30. Okay, that's all this is, rate of change in velocity. Okay, so my rate of change in velocity here is positive 5, and it says until it reaches 35. Well, there's that. There's my 35. Okay, so now it's on the freeway. This is meters per second, so that is an acceptable freeway speed. It's not miles per hour. But yes, this would be what your data would look like for the scenario described here. It would take the car 3 seconds to reach that velocity. How does the distance that the car travels in a second change as its speed changes from 20 meters per second to 35 meters per second? Is it traveling the same distance each second? No, not anymore. We're not looking at constant velocity anymore. Okay, and so if you were getting faster, it's going to be traveling that's the definition here. 20 meters per second means it travels 20 meters in 1 second. 35 meters per second means it travels 35 meters in 1 second. So how does that distance the car travels change? It travels farther per second as it's getting faster. Okay, how many seconds did it take the car to reach 35? We just saw that. It took it 3 seconds before. This is a different set of data. This car was driving for a few seconds before the ramp. Okay, but this one says a car is traveling at 20 meters per second from 0 to 2 seconds when it enters a freeway ramp where it accelerates at a rate of 5 meters per second every second until it reaches 35 meters per second. Okay, so I've added a couple seconds beforehand, otherwise it's the same data. A data table for this might look like this, over here to the right. What would the XT graph look like? Well, I already have it there. But the first part of it, you have a straight line, just like we did in those constant velocity graphs. Okay, because we have a uniform change in position each second, 20 meters each second. And so this is a straight line. However, after that, it starts to get faster, and on a position time graph, slope is speed. And if it gets faster, your slope has to get steeper. And that is what you guys saw in the simulation in the digital lab yesterday as well. You saw curves on those position time graphs. As that velocity changed, your slope has to change, because that is what slope is. Okay, so this is what that velocity time graph might look like, where the slope is changing and getting steeper as the velocity is getting higher. Okay, and we just said that. Why does the line curve? Again, it's going to curve because of the fact that there's acceleration happening here. If you have acceleration, your position time graph will have a curve on it. And the meaning of the slope, we just talked about that too. The slope represents the velocity. So the fact that the curve is there means that the slope is changing, and thus the velocity is changing, and that's how you know that you have acceleration happening. Okay, I've added in some little arrows to my picture so you can see that slope changing. And I think there was an image like that yesterday too. Okay, if you look at the slope at any given point and draw like a tangent line to that point, you can see that this is steeper up here than it was down here. All right, so if speeding up means that the slope gets steeper, which of these graphs shows an object slowing down? Take a moment and look at those. There's 4 of them there, A, B, C, D. Which one do you think, and you can ask your neighbor and discuss it with them if you're not sure, but which one do you think shows an object slowing down? I'm going to give you guys 22 seconds to discuss with your neighbor, and then I'm going to call on somebody. So have an answer ready in case it's you. All right. What do you think, Ainsley? Which of these show an object slowing down?
C.
Okay, so it says here, which one, if speeding up means the slope gets steeper, right? So is C getting steeper? C does get steeper. Yeah, it starts out almost horizontal and it gets steeper down here. So C would actually show something speeding up, which we don't want. We want slowing down. So which one shows the slope getting less steep? You want to help her out?
B.
Yeah, B. Look at B. The slope starts out steep, but up here it's almost flat. Okay, and so if it gets flatter, more horizontal, that means it's slowing down. So any graph that gets more horizontal is going to be slowing down. B slows down. Does anything else up here show slowing down? D. B and D both show an object slowing down. Okay, B is an object that is moving forward and slowing down, and I know that because forward means positive slope. So it's moving forward, but slows down. D shows an object moving backward and slowing down. Okay, but both of them show an object slowing down. And again, we're looking at the slope here. We're looking for a slope that gets less steep because speeding up means the slope gets steeper, then obviously slowing down must mean that it gets less steep or more horizontal. Okay, the slope is becoming more horizontal, which means the distance traveled in a second is less. This means the speed is getting slower. However you want to write that if you're jotting this down. All right, what do you think the difference is between B and D? I kind of answered that one for you, but B, again, is moving forward because it has a positive slope, but that slope is still flattening out, so it's moving forward, but it's slowing down to a stop. D is moving backwards, but slowing down to a stop. If it goes completely horizontal, they've stopped. That is the difference here. Okay, so because B has a positive slope, it's moving forward. Because D has a negative slope, it's moving backward, but both of them are slowing down. All right, which graph or graphs show positive acceleration? This is a trickier question, but we went over 4 scenarios, right? If you wrote them down already, you already know that you have positive acceleration. The easy one is you have positive acceleration when you have an object that is moving forward and speeding up. So let's start there. Which of these images shows something that is moving forward and speeding up? A, B, C, or D? A. Moving forward because it has a positive slope. Okay, and that's this one. What happens when an object moves forward and speeds up? So this one has a positive slope. It's moving forward, and that slope gets steeper. So maybe it's like this. It goes from 2 to 4 to 6 meters per second. My slope changes from 2 to 4 to 6. Okay, and so A would be an example of positive acceleration, but you also get positive acceleration when an object moves backward and slows down. So something that starts out at negative 15 and then negative 10 and then negative 5 and it flattens out. Okay, and so if you have something moving backward and slowing down, we already talked about how that's what was happening in graph D. So both graph A and graph D show acceleration is positive. That is a harder question to answer because you have to remember a lot of things, which is why it would be really helpful if you had it written down somewhere. That would be nice to look back at potentially. Okay, because it is kind of difficult to answer this question from an XT graph. I will tell you this though, it is a lot easier of a question to answer if you have a VT graph in front of you. Okay, and we'll look at some of those later on. Are there any questions about this before we move on? Okay. All right, A and D, we already said that. All right, and I just said that. This question is much easier to answer if we look at a VT graph instead of a position time graph. Okay, because acceleration is the rate and change of velocity, this means that the line on a VT graph will have a slope, and that slope will tell me my acceleration because that's what the definition of a slope is. Okay, is that it is change in y over change in x. And on this graph, change in y is change in velocity over time. That is the formula, the definition of acceleration. So let's see if we can draw the corresponding VT graphs for each of these. This position time graph for A, there are 2 questions you want to ask yourself to help you draw your VT graph. What direction is the object going? And is it speeding up or slowing down? So looking at A, this object is going forward, and I know that because I have a positive slope, and it's speeding up, and I know that because the slope gets steeper. So if I want to show something that's moving forward and speeding up on a VT graph, forward is going to be up here in the positive region. That's how a VT graph works. I have positive velocities. I'm above the x-axis. Speeding up means I have to move away from 0 because 0 means I'm not moving. So obviously the farther I get from 0, the faster I am going. Okay, so I'm going to put my line up here, something like this. If I start from rest, it looks like that. Okay, and this graph looks pretty horizontal at the beginning, so I'm going to start from rest. But this would be the corresponding velocity time graph for this position time graph. Okay, let's try this one now. What direction is this object going, forward or backward? Backward. Is it speeding up or slowing down? Slowing down because it gets more horizontal, less steep, however you want to think of it. So backward means I'm down here. Slowing down, guys, what's the slowest speed you could go? Or maybe not go? 0, right? If you're going 0, you're not moving. So if you're slowing down, you need to approach 0. If you stop, you're going to touch that 0 line. Okay? So slowing down looks like this. Okay? Because I'm going from a velocity of maybe -5 to -4 to -3 to -2 to -1 to 0. Okay, that's slowing down in the negative direction. And so that's what this graph looks like. And what do these two graphs have in common? Well, they both have a positive slope. And therefore, they both represent positive acceleration because, and you might want to write this in your notes, the slope of a velocity time graph is acceleration. Guys, think about the definition for acceleration and think about the equation for slope, rise over run. Okay, change in y over change in x. Well, it's not y, it's v. Change in v over time. That's the definition of acceleration. So your slope is acceleration, and look at these slopes. Both of them are positive. That is so much easier to look at than those xt graphs. Okay, so if I ask you which of these shows positive acceleration, you might want to sketch the VT graph because you can see it immediately as soon as you see that slope. All right, so let's talk about drawing graphs. Okay, we've already talked about xt and vt graphs. We're going to add a third graph today, and that is the acceleration time graph. We didn't have to draw those in the last unit because we didn't have acceleration, but now we do. So we're going to go over pretty much every possible scenario that you could be asked to graph, starting with something that's not moving. Okay, we already know what something that's not moving looks like. We did this in the last unit. If you're not moving, your xt graph is going to have a horizontal line. Anywhere, any y-intercept is fine. Okay, it just depends on where that object is stopped. So this object is stationary at a position of, I don't know, 6 meters, whatever. But it doesn't have to be there, it depends, okay, on that scenario. My VT graph, if I have 0 velocity and I am not moving, well, guess what? My line is at 0, and it does have to be on the x-axis because otherwise it's moving, because this shows velocities. I need my velocity to be 0. Okay, my acceleration graph, again, the slope of this is going to tell me this. Same thing here, by the way. Slope of this is 0. Guess what? This is 0. Slope of this is 0. Guess what? This is 0. If it's not moving, it's not accelerating. Okay, so I already knew that. So I need 0 acceleration the whole time. It would look like this. This is why we didn't draw them in the last unit, because all of them would have looked like this. Okay, so object with 0 velocity. Velocity is 0. Acceleration is 0 according to these graphs. Okay, what about an object with a constant velocity that is moving forward? Well, again, we've done this in the last unit. There's an example xt graph. Again, any y-intercept is fine, but you have a positive slope, okay, in a straight line. On my VT graph, again, the slope of this tells me this. So maybe this is +3. Cool. Guess what? This is up here then at +3 or whatever. Okay, but it's constant velocity, so you're going to have a horizontal line because my velocity is not changing. My acceleration, though, if I have constant velocity, is 0, and so my AT graph would still look like this. So this is, again, the same exact AT graph we saw for the last one, which is why all of them would have looked like this in our constant velocity unit. So if you have something moving constantly forward, constant velocity forward, this is what those graphs look like. This is an example of an object with positive velocity, but 0 acceleration. All right, let's look at the next one. By the way, if I'm going too fast for you, this is slide 19. You are welcome to open it up on your own screen. Constant velocity backward. Well, there we go. Negative slope, straight line. Again, any y-intercept is fine. Okay, the slope of this tells me this. So if this is -3, then so is that. Okay, but this is at a constant velocity, so it needs to be a horizontal line. And again, the slope of this tells me this. This is a slope of 0, and again, it tells me here it's constant, so guess what? It looks like that. Again, all of our constant velocity graphs from last unit produce the exact same AT graph because there's no acceleration. So again, negative velocity, 0 acceleration. So let's get to the new ones. Speeding up while moving forward. So this is new. You saw it yesterday, we saw it already a couple times today, but if we want something that is moving forward on our XT graph, again, we know that forward means positive slope. And if we want it to speed up, we know that that means the slope has to get steeper, and that's what I've drawn. Now, does it have to look exactly like that one? No, but you need that basic shape, okay? On my VT graph, if I want to show something speeding up moving forward, again, I have to be in the positive region of the graph above the x-axis for it to be moving forward. If I want it to speed up, I need a line with a slope to it to show that my velocity is changing, and that line needs to slope away from 0. Okay, and that's exactly what happens here. So maybe this velocity goes from 1 to 2 to 3 to 4 to 5, so on and so forth. Again, the slope of this VT graph shows me my acceleration. This has a positive slope, so this has a positive acceleration. If this slope is +2, well then this is +2. Okay, so you can use that to find the next one. This is an example of something with positive velocity and positive acceleration. Okay, when these two variables have the same sign, and this might be a note you want to add to your notes as well, if your velocity and your acceleration have the same sign, they're both positive, they're both negative, that means your object is speeding up, okay, because that means they're working together. When the signs are opposite, it means they're slowing down, okay, and you're going to see that in a minute. All right, here's speeding up backward. Okay, backward means negative slope here. Speeding up means that slope has to get steeper. Okay, so it needs to have that shape because it needs to get a steeper and steeper slope. On my velocity time graph, backward means I am down here. And again, speeding up means it needs to move away from 0, and so we're going to slope it away from 0. Again, if it starts at rest, it starts here. Otherwise, it starts somewhere else, but it still has that shape to it. My acceleration time graph, I'm going to use the slope of my VT graph to find it. This is a negative slope. I don't know what it is because there's no numbers. Maybe it's -6. Then guess what? This is at -6. Okay, so you're going to draw it accordingly. But you know it's negative, and we only deal with constant acceleration in here. So you should always have straight lines on your VT graph and horizontal lines on your AT graph. Again, this is an example of something with negative velocity and negative acceleration. Those signs are the same. This should be speeding up. It is. Okay, look at that. Double check yourself. All right, slowing down while moving forward. Again, forward means positive slope on my XT graph. Slowing down means that slope needs to get more horizontal. The shape looks something like this, because it starts out with a steeper slope in the forward direction and flattens out. Again, on my VT graph, forward means I'm up here. Slowing down means I need to approach 0. Something like this is what you would expect to see on your VT graph. And again, use the slope of this to find this. This is a negative slope. So guess what? This is negative acceleration. And again, this is an example of something with positive velocity but negative acceleration. Those signs are opposite. That means they're working against each other. That means you're slowing down. Double check it. Okay. I think this is the last one. Slowing down while moving backward. Again, backward on my XT graph means negative slope. Slowing down means that slope needs to flatten out. Okay, on my VT graph, backward means I'm down here. Slowing down means I need to approach 0. Looks like this. Okay, and the slope of this line is positive. So guess what? My acceleration is positive. And guess what? Because I have negative velocity and positive acceleration and the signs are opposite, it means I'm slowing down. Okay, so those are pretty much all the possible graphs. Now, you could see graphs that have components of each of these, and it has different stages of motion, and that's fine too. But does anybody have a question about the graphs? Definitely want to have that stuff written down though. All right, guys, for the remainder of your class period today, you have an assignment. It's not in my open math, sorry, that's from last year. I wish it was. It works so much better. But anyway, you need to go to Schoology, and you're looking for the assignment 202.1, Acceleration Concepts Problem Set. It is a Google Sheet, so whenever you open it up in Schoology, you should be able to see that 202.1 Acceleration Concepts Problem Set. There are tabs at the bottom. Make sure that you're working on the correct one. Otherwise, you're going to be working on something you don't know how to do yet. Okay, so you should be working on the one that says 202.1, and you should be finishing this up today or by 11:59 p.m. tonight. However, please don't submit your Google Sheet because there are 2 more tabs. Okay, so just fill it out and have it done by tonight, but you do not have to click submit. Okay, so that's what you have for the rest of the period. So I'd recommend that you use the class time that you have left because, guys, we still have 15 minutes. So use it. And that way, if you open it up and you get started and you're not sure what to do, you can ask a neighbor, you can ask me, but you have the opportunity to ask questions. So go ahead and get to it. And if you have questions for me, please let me know.